Hello guys. So in this video we are going to see the numericals based on the air conditioning. Fine. So here is the statement given for the numerical that an air conditioning is designed for a hall when following data is available. So we are supposed to design one air conditioner for a hall. So for that hall the conditions are given like outside conditions at 35 degree Celsius dry bulb temperature and 26 degree Celsius wet bulb temperature. So these outside conditions are nothing but the conditions of the atmospheric air. Then the inside conditions, that is 27 degree Celsius DBT and 55% RH. So inside conditions are nothing but the conditions which are going to maintain inside the room or the space which is to be cooled. In this case it is a hall which is to be cooled. So inside a hall the conditions are maintained at 27 degrees Celsius DBT and 55% RH. Then in the hall the sensible heat which is generated is given as 35 kilowatt and the latent heat is given as 10 kilowatt. We know that in the room the total heat is generated and the AC will be required to remove that particular generated heat so that the temperature of room will be maintained at a required state. Okay, so here the total heat is the combination of sensible heat and the latent heat, or it is the sum of sensible heat and the latent heat. So that total heat is given over here as a sensible heat as 35 and latent heat as 10 kilowatt. Okay, then they have given the bypass factor for the cooling coil, it is 0.2. The statement is given here like the 80% of a room air, that is the hall, the air from the hall is recirculated and mixed with the 20% of fresh air before the conditioner. So before the conditioner, it means that before the cooling coil. Conditioner is nothing but the cooling coil. So we are supposed to evaluate the RSHF, room sensible heat factor. So we know the formula for it. Then the supply air condition, ADP, apparatus dew point temperature, and the cooling coil capacity in terms of refrigeration. Now we'll see the solution of this particular problem. However, whenever you are solving such type of problem, the first and foremost important step of this particular problem is to draw the schematic based on the given statement. Okay, so here what I am going to do, I will draw one schematic. Okay, assume that this is the hall basically which is to be cooled. Okay, this is the hall which is to be cooled. Okay, hall or room you can say. Then I am having the conditioner over here, air conditioner over here. For simplicity I am assuming it is the air handling unit in which there is the cooling coil. So this is the cooling coil, this is the cooling coil. Then after cooling coil there is the blower. So this is the fan or the blower, and over here this is the supply side. So from here the air will be given to the room. Okay, so this is the supply side, and from here the air will be taken back. Okay, that is the return air. This is the return air. Now this air is getting mixed with the fresh air before the conditioner. So this is the conditioner, and assume that there is the fresh air coming over here from this particular passage. Okay, so this is the fresh air which is at a state number 1. Okay, so that air is coming over here and going to get mixed with the return air over here before the conditioner. So this is the conditioner or the cooling coil before which the return air, this is the return air, and the fresh air is getting mixed. Fine. Assume that I am maintaining the room or the hall at a state number 2. I am maintaining the room or the hall at a state number 2. So obviously the condition of air which is coming from the room will be the state number 2 only, because I'm maintaining the room at a state 2. Assume that I'm maintaining the room at a 24 degrees Celsius and 50% RH. So in that case, when I'm maintaining the room at 24 degrees Celsius and 50% RH, it means that the maximum temperature and the humidity reach in the room will be 24 and 50%, and at this particular state only the air will be taken back. Okay, obviously for this particular hall the conditions are given different conditions. Okay, but time being you can assume that I am maintaining the hall at rather the room was maintained at 24, so at 24 only the air will be taken back. Okay, so this is how the meaning of it basically. Just a minute. Okay, so here, just a minute, I will erase these things, otherwise you'll have the confusion. Fine. Okay, so now the condition of air which is taken back from the room is nothing but the return air will be the state number 2. Now when the air at the state number 1 and air at the state number 2 both are getting mixed, obviously the mixing state will be totally different than the state number 1 and 2, that is I am calling it the state number 3. So this is nothing but the mixing section. This is the mixing section or the mixing chamber where the air is getting mixed with the rather return air and the fresh air is getting mixed. Now when this particular mixed air is passing over the cooling coil, obviously this air or the mixed air will be giving its heat to the refrigerant which is flowing inside the coil, and hence the air will get cooled, obviously lesser, having temperature less than the state number 3. So when the air is coming out from the cooling coil, the state will be different than the state number 3. I am calling that state as state number 4. Now at a state number 4, air will be going to the fan. Okay, so obviously there is no any change in the state of the air because of the fan operation. So the exit of fan will be the state number 4 only, and that exit of fan is given to the room over here. So obviously if I see the state of a supply air will be the point number 4 over here. So this is the point number 4 only. Okay, so at point number 4 the air will be supplied to the room. So assume that if I am maintaining the room, this hall is maintained to be at 27 degrees Celsius, then the supply condition or the supply temperature will be definitely less than the 27 degrees Celsius for the cooling purpose. So this is how you are supposed to draw the schematic. This is very much important. If you are through with the schematic, then you can easily solve the problem whichever is there. Okay, now I am writing the percentage. So fresh air percentage is 20% and the return air percentage is 80%. Okay, so here I am writing it is 80%. Now see that this 80% return air plus 20% fresh air, so at point 3 I will be having 100% of mixed air. So that 100% of mixed air will be supplied to the room over here. Okay, so this is how the 100% of air will be supplied to the room, and that air 100% air will be mostly or generally called as the dehumidified air, will be called as the dehumidified air. Okay, so now we will write down the given data over here one by one. Obviously I will need the psychrometric chart as well to solve the problem. Okay, so outside condition, that is the condition at point number 1, they have given as 35C dBT and 26C WBT. Okay, so I am not writing that again and again. When I go for the psychrometric chart, I will use that data. Inside condition 27C dBT and 55% RH. So the room is maintained at 27C dBT and 55% RH. Okay, that is the state of room or the room is to be maintained. Fine. Then the sensible heat generated inside the room they have given, which is equal to 35 kilowatt. Latent heat in the room is given, that is I think 10 kilowatt. We will just confirm. Yeah, it is 10 kilowatt. Bypass factor is given as 0.2. Okay, fine. Okay, now that percentage already you have written, 80% is return air or the recirculated air basically, and 20% is fresh air. Now we will go one by one. The first what they have asked is the RSHF. Okay, first bit is RSHF. So RSHF is nothing but the room sensible heat factor, and it is given as room sensible heat divided by room sensible heat plus room latent heat, which is nothing but the room sensible heat divided by room total heat. Room total heat, because sensible heat plus latent heat is nothing but the total heat. Fine. So here obviously they have given room sensible heat, which is nothing but the sensible heat. Obviously it's a room sensible heat and room latent heat. So RSH is given as 35 kW. RSH is 35 plus 10. Okay. If you calculate these things, we will get the RSHF. Okay. So if you calculate that value, you will have the answer about 0.77. Okay. And let us you please do the calculation. So 45 divided by 35 divided by 45. Sorry. So it is 0.78. Comes around to be 0.78. So this is your first answer. This is your first answer. Fine. The next one. The next we are supposed to calculate the supply air condition. Fine. So to get the supply air condition, obviously I need to make use of the psychrometric chart. Fine. So I am having the psychrometric chart over here. What I will do, I will just go on plotting the points over here, outside condition, inside condition. Okay, all those points I'll be plotting. So they have given the outside condition as 35C dBT and 26C WBT. Fine. So here this is the 35C dBT line, and we need to see for 26C WBT. So this is 25C WBT, and here it is 26C WBT. So this point, okay, this point is nothing but the outside condition. This point will be representing the state number 1. Okay, then the inside condition is 27C dBT and 55% RH. So this is 25, 26, 27 and 55% RH. Now we know that these curves are nothing but the relative humidity curve. So this is 55% RH. This is 55% RH and this is 27C dBT. Correct now? Yeah. So here I'll be having the point number 2 somewhere over here. So this is the point number 2. This is the point number 2. Fine. Or I can, okay, fine. Now I'll just join this particular line. This I am joining. Now we know that the mixed condition, that is the mixing of outside air and mixing of room air, that is the mixed condition, point number 3, will be always falling on the line 1, 2. Okay. So where to get that we will see. Now I need to get, obviously when you see the supply air condition, here this diagram already we have studied. So this point number 4 is the supply air condition, the given over room supply air condition. So to get this point number 4, what are the lines I need? One is the RSHF line and second one is the GSHF line. So intersection of RSHF line and GSHF line is nothing but the supply air condition. So first I will get the RSHF line over here. So we know that the procedure to get the RSHF line, that first to calculate the RSHF. So that already we have calculated and the value is 0.78. So this is 0.75, 0.8. So somewhere over here you have the 0.78. Okay, this is the RSHF. RSHF is equal to 0.78. Now the second step, next step is to connect this RSHF value or the RSHF with the alignment circle. Now you can see over here there is one dot drawn over here on the chart, which is at a 26C dBT, 26C dBT and 50% RH. This is the 50% RH line. So this particular dot is basically called as alignment circle. This is nothing but the alignment circle. Okay. So obviously this value, this circle may be different on a different chart. Maybe you'll find this at 2550 on some other chart or 2650 on other chart. Okay, so here it is 2650. Whatever is the given, you consider that alignment circle. Okay, now So for second step is that you calculate the first step is to calculate the RSHF, and second step you connect this particular RSHF with the alignment circle. Okay, so I am just connecting now. I don't have the scale, or rather I can't draw the straight line over here, so just consider that particular thing. Fine. So this is the line I have joined. So this line is known as base line. Okay, I'll go one by one again. The first step, I calculate the RSHF. Second step, I have connected this RSHF with the alignment circle, and the line which I have drawn is known as the baseline. Now we can draw the RSHF line. So that RSHF line will be starting at point number 2. It will be starting at point number 2 and will be parallel to this particular baseline. Okay, so I'll be drawing one line over here starting from point number 2, and it will be parallel to this particular baseline. So something like this I'll be having the line over here. Okay, something like this. Okay, so this is nothing but the RSHF line. This is RSHF line. Fine. Now I got the RSHF line. So if I get the GSHF line, I can get the point number 4 over here. Okay. So to get the GSHF line, obviously I need to have the mixed condition. Okay, we'll just go back over here. Now to get the mixed condition, we know that we can use the equation for mixing of two air streams. Okay, so if you remember, we were having that particular mixing of two air streams equation as mixing of two air streams, where I have considered the fresh air and return air only. It was something like M1 by M2, which is equal to H3 minus H2 divided by H1 minus H3. H1 minus H3. Okay, that is what the equation given over here. Now what is M1 and M2? M1 is nothing but the mass of fresh air, and M2 is the mass of return air. H3, H2, H1. So H3 we don't know basically. This value we can get from this entire equation, and H2 and H1 we can get it from the psychrometric chart. So that I can write down over here. So the value of H2 and H1 from the psychrometric chart. Okay, we'll go back to the psychrometric chart. So if I see the point number 1, with respect to point number 1, the enthalpy is about 80.5. Okay, it is about 80.5. So this is nothing but the H1 value. This is the H1. Okay, 80.5 kilojoule per kg of dry air. Okay, so that is the H1, and let us see what is the H2 value. So here it is point number 2, little bit upper of this particular line. This line is 55, 56, 57.5, so about 58. It is about 58. See here, 58. So if I draw one parallel line to this particular WBT line, that line will be intersecting over here. So this is nothing but the H2 value, so which is about the 58 kilojoule per kg of dry air. Fine. So now what I can do, I can put those values in this equation, but before that I need to have the M1 and M2. So here I am considering the percentage mixing of those air. So here 20% is the fresh air and 80% return air. So what I can do, I can consider the M1 as 0.2. So I can write this equation as 0.2 as M1 divided by 0.8 as the return air. Okay, M2 is nothing but the return air, which is nothing but the 0.8. See, this is M2 and this is the M1. Okay, here I am having M1, here I am having M2. Okay, so M1 is fresh air 20%, so 0.2. M2 is return air, which is 80%, so 0.8. Okay, which is equal to H3 minus H2. Now H2 value I am having. Okay, so I'll just use the eraser over here. Just a minute. Fine, I'll have the eraser. H2 value I am having. So I'm just putting that value as it is. So H2 is 58. Okay, it is 58 divided by H1 is 80.5 minus H3. Okay, solve this particular equation and we can get the value for H3. Okay, so we will solve this. Let's say H3 minus 58 into 0.8 is equal to 0.2 into 80.5 minus H3. Okay, so 0.8 H3 minus 58 into 0.8. You can do the calculation on the calculator. So 58 into 0.8, it is 46.4, 46.4, which is equal to 0.2 into 80.5, or 0.2 into 80.5, it is 16.5, sorry, 16.1, it is 16.1, okay, minus 0.2 H3. I'll take H3 terms on one side, so it is 0.8 H3 plus 0.2 H3, which is equal to 16.1 plus 46.4. So it is obviously H3 is equal to 46 and 16, 62.5, 62.5 kilojoule per kg of dry air. Okay, I'll go back to the psychrometric chart now. I have got the value of H3 as 62.5. Okay, so I have got the value of H3 as 62.5, so it is 61, 62 and 63. Somewhere over here you will have the H3. Here is the H3. Now from this point I will draw one parallel line to these WBT lines. Okay, I'm just drawing the parallel line over here. Just a minute. Okay, something like this. Okay, I'll draw the parallel line. Now wherever that line is intersecting to this particular line 1, 2 is the point number 3, because we know that the mixed condition will be always between the point number 1 and point number 2, because the mixing is of fresh air, that is point number 1, and the return air, that is point number 2. So this point number 3 is nothing but the mixed condition. It is nothing but the mixed condition. Fine. Now I will get the GSHF line. Once I get the GSHF line, I can have the supply air condition. So I'll just go back to this particular standard line. Now we can see over here, the GSHF line is starting at point number 3 over here, okay, and it will be coming down, it will be crossing the RSHF line, and it will be intersecting to the saturation curve. Now wherever that line is intersecting to the saturation curve, I will get the apparatus dew point temperature ADP. Okay, however, if you see over here, which is very important, that the distance between ADP and point number 4 is the bypass factor, and ADP to this particular total distance is 3. Okay, so that is the 1. The ADP to 3 will be, the distance is equal to 1. Okay, because bypass factor plus 1 minus bypass factor. Okay, because this distance between 4 to 3 is 1 minus bypass factor. Okay, that is the efficiency of the coil. Okay, whereas this is the inefficiency. So bypass factor plus 1 minus bypass factor. So this total length ADP to 3 will be 1. Okay, so this distance divided by total distance has to be equal to the bypass factor. But this is what the bypass factor divided by the 1, the distance. I will write down over here equation, length ADP to 4 divided by length ADP to 3, ADP to 3. Okay, now here length ADP to 4 is what? Bypass factor, divided by length ADP to 3. ADP from ADP to point number 3 is the 1. So what is this particular equation then? So this length ADP to 4 divided by length ADP to 3 is nothing but equal to the bypass factor, is nothing but the bypass factor. So what I will be having, that is this distance ADP to 4 divided by total distance has to be equal to the bypass factor, Now this particular GSHF line you should be drawing with the trial and error method. That is the only way to draw this GSHF line. you will be starting point from the point number 3, and you will be adjusting the scale such that this distance ADP to 4 divided by the distance ADP to point number 3 has to be equal to the given bypass factor. In our case, the given bypass factor is 0.2. So the ADP to 4 divided by ADP to 3, that distance has to be equal to the 0.2 or close to 0.2. So you are supposed to adjust the scale by fixing this particular 0.3. So you'll be fixing the 0.3 and you'll be adjusting the scale such that this distance divided by the total distance will be equal to the bypass factor. For example, I am adjusting the scale such that the ADP to 4 is equal to 2 centimeter and the total length ADP to 3 is equal to 10 centimeter. So I'll be having the ratio 2 divided by 10, which is equal to 0.2. So that is your GSHF line. Okay, so this is how you are supposed to do the trial and error only. Okay, so you'll be adjusting the scale to get this distance. The ratio of this distance is equal to the bypass factor. Okay, we'll go back to the psychrometric chart over here. Now here the bypass factor is, let's say, 0.2. Okay, so by doing this particular adjustment, assume that I'm getting somewhere over here the line something like this. Okay, so this is nothing but the GSHF line. This is nothing but the GSHF line. Okay, so this is the GSHF line. This is nothing but the GSHF line. Assume that this distance, this is the point number 4 now. Okay, supplier point. So this and this particular point which is intersecting to this particular saturation curve is the ADP. So ADP to 4, okay, divided by ADP to point number 3 has to be equal to the bypass factor 0.2. Likewise, you are supposed to adjust the scale, or should be close to the 0.2. So in my case, assume that I am getting this particular line, this distance is divided by the total distance. Okay, that is coming to be 0.2. Now what I will do, I will go for the next thing. So obviously I have got the supply air point, that is the point number 4. Okay, see in the schematic you can see the point number 4 is nothing but the supply air point, correct? So with respect to this point number 4, from the psychrometric chart I will note down the various points. So likewise at point 4, what is the dry bulb temperature? So it is about to be 18 degrees Celsius. Okay, with respect to this, the WBT is about 16.1 something. Okay, likewise I will just go on noting down the answers. So let's say at a point at supply air condition, let's say supply, this is the supply air condition. So dBT at 0.4, which is equal to it was 18 degrees Celsius. WBT at 0.4, which was equal to 16.1 degrees Celsius. Guys, you may get a different answer from this. I am just showing you the procedure. Okay, don't rely on the answers which I am writing down over here. You use the psychrometric chart, draw the proper parallel line to the baseline, draw the proper GSHF line by using the given bypass factor. Then and then you can get these answers. Fine. Okay, and if you don't understand, you can comment through this particular video. I'll just explain again what is the procedure. Fine. Okay, then with this particular point, I will note down what is the specific humidity. So the specific humidity is let's say this is the line. Specific humidity, I should go horizontally towards right. It is 0.012, 0.011, 0.015. About 0.015. So W at 0.4 is 0.015. Okay, it is 115, sorry, 0.0115. It is kg per kg of dry air. Then I supposed to find out what is the relative humidity at 0.4. Okay, let's see. Sorry. So with respect to 0.4, the relative humidity, this is the relative humidity curve. is of 80%, 85%, and I'm having the point between those two, so it is 82% around. Okay, I can say it is about 82.5%. okay, this is again in between, so I'm just writing that particular value. Okay, now the next one. Okay, what are the things? RSHF we have got, supplier condition we have got. Now we will find the ADP. Okay, so ADP, as I said, if you extend this GSHF line, wherever it is intersecting this particular saturation curve, that point is nothing but the apparatus dew point temperature. Already I explained that in the previous videos. Okay, so this is 10 degree to 11, 12, 13, 14. So it is around 13.3 or 13.4 degree Celsius. So the ADP over here, the third answer, ADP is equal to 13.3 degree Celsius. It is again, I am saying that this is not the correct answer. You get the correct answer. I am just showing you the procedure. And lastly, I need to find out the cooling coil capacity. The cooling coil capacity. Fine. So to get the cooling coil capacity, okay, just go back to the psychrometric chart. Now fine, before, yeah, schematic diagram. So here between which point or across cooling coil, what are the 2 points? You can see the point number 3 and point number 4. These are the 2 points across the cooling coil. Okay, so between this point only the cooling process is taking place. So from point number 3 to point number 4 only the cooling is taking place. So these points are responsible for the load on the cooling coil. Okay, so if I have, let's say, cooling coil capacity, if I write H3 minus H4, okay, so this answer will be in kilojoule per kg, because enthalpy having the answer, unit as kilojoule per kg. This answer will be in kilojoule per kg. If I multiply this particular kilojoule per kg by, let's say, mass of air, let's say MD, dehumidified air, then obviously this mass, let's say, in kg per second. Assume that the mass is in kg per second into kilojoule per kg. Okay, kg get cancelled. Finally I will remain with kilojoule per second. So this is the cooling coil capacity in kilojoule per second, which is nothing but the kilowatt. And simply I can convert this kilowatt to tons of refrigeration by using the relation 1 TR is equal to 3.5 kilowatt. Okay, or else if you are using this particular mass in kg per minute, let's say, if you are using this mass in kg per minute, you will get the answer in kilojoule per minute. So in that case you can use the relation 1 TR is equal to 210 kilojoule per minute. Okay, anything you can do, but only the thing, whatever unit you are using over here, use the proper conversion factor over here. Fine. So now you can get that the cooling coil capacity will be whatever the mass of air passing over the cooling coil, that is the dehumidified air mass, into the enthalpy difference across the cooling coil. This equation, I always recommend that you write this equation by using the schematic diagram only. Okay, now H3 and H4, already those values are with you. Only thing you need to get the mass of dehumidified air. Okay, so here I am writing the equation again. Cooling coil capacity is equal to mass of air or mass of dehumidified air into H3 minus H4. These two values we can get it from the psychrometric chart. We are supposed to get the mass of dehumidified air. Okay, MD is the mass of dehumidified air. Okay, now to get this particular mass, we'll go back to the schematic again. Now we know that this dehumidified air MD is supplied over here, because that mass MD is passing over the cooling coil, and the same mass is flowing through the blower, and the same mass is supplied to the room. Whatever MD mass is supplied over here, that air is responsible to take the heat generated inside the room. We have already seen the working of AC, where the air, cold air which is supplied over here, the cold air is nothing but the dehumidified air over here. So that air is responsible to take the heat from the room, and that air will be taken back over here. Correct? So whatever heat is generated inside the room has to be taken by this dehumidified air. Okay, so I can write one equation that whatever total heat generated in the room will be equal to the heat absorbed by dehumidified air. Now what is the total heat generated inside the room? That is nothing but the sensible heat, room sensible heat plus room latent heat. That is the only total heat generated inside the room, which is equal to heat absorbed by the dehumidified air. So what is the heat absorbed by the dehumidified air? We'll go back to the schematic. Let's say the mass of dehumidified air is md. Md mass is supplied over here, and if I want to have the Q, that is m into delta H. Correct na? So delta H nothing but the enthalpy difference, m is the mass. Here I am supplying the mass as md in the room, and across the room what is the enthalpy difference? So here it is md into across the room. What is the enthalpy difference? That at the room or to the room, air is supplied at point number 4 and taken back at the point number 2. So this is the enthalpy change in the air. When it is entering to the room, the enthalpy was 4, but when the air is returning from the room, the enthalpy is 2. So that is a change in the enthalpy in the room for that particular dehumidified air. So here I will be having the enthalpy difference as H2 minus H4. H2 minus H4, that is nothing but the heat absorbed by the dehumidified air. Okay, so the same equation I can write down over here. So heat absorbed by the dehumidified air is the mass of dehumidified air into the enthalpy difference across the room, that is H2 minus H4. Now both these values you have, H2 is known, H4 is known, RSH, RLH, both these things known. You can calculate the MD. Okay, so let's say I'm calculating the MD over here by doing the calculation. Okay, so assume that you have the RSH and RLH is 35 plus 10, that is 45 kilowatt. 45 divided by H2, value of H2 is 58 minus H4 enthalpy at point number 4. Okay, so we are not written over here. So enthalpy at point number 4, just go back to the psychrometry chart. Here you can have H4 is about 45, 46. I think we have written somewhere H4. H4 we are not written. Fine, so H4 is about 46. Fine, H4 is about 46 kilojoule per kg of dry air. Okay, so it is 58 minus 46. Okay, so that answer is coming around to be 3.75. This MD is 3.75. Okay, so what I have done, I will just explain you again. RSH is 35 kilowatt plus RLH is 10 kilowatt, which is equal to MD into H2 is 58 and H4 is 46. So from this I can get the MD as 3.5. Now what the unit will be? The left hand side is in kilojoule per second or kilowatt, and right hand side is kilojoule per kilojoule per second over here, because left hand side and right hand side has to be equal. So whatever unit for mass of air I'll be getting, it will be in kg per second, because these values are in kilojoule per second. So per second values are there, so the mass also will be per second. So this will be kg per second. This will be kg per second. So once you get the mass of dehumidified air, you can put that mass in this particular equation over here to get the cooling coil capacity, which is equal to 3.75 into H3. H3 already we have noted down, we have rather calculated, it is about 62.5. okay, here it is the value 62.5, this is the value, so I'll write 62.5 minus H4 is 46. okay, so why H3 minus H4? Because between or across the 3 and 4 only the cooling process is taking place. So I'll just do the calculation. 3.75 into 62.5 minus 46. The answer I am getting is around to be 61.87. This is in kilowatt. Because this is in kg per second, this is kilojoule per kg. So kilojoule per second is kilowatt. Convert this kilowatt to tons of refrigeration, because they have asked the answer in kilowatt. So we know that the relation 1 TR is equal to 3.5 kilowatt. So I need to divide this particular answer by 3.5 to get in tons of refrigeration, and the answer is coming around to be 17.67 tons of refrigeration. So this is your final answer. So to cool that particular hall, which is generating 35 kilowatt sensible heat and 10 kilowatt latent heat, I need to have 17.67 tons of refrigeration. So this is how you will be solving the numerical based on the air conditioning. Okay, these are very simple numericals, the straightforward numericals. Okay, now I'll just give you one brief about over here. Suppose in this particular problem, if the ADP is given, directly what you will do, you will mark the ADP over here, and directly you can connect the point number 3 with the ADP. So in that case, you need not to go for that what you can say, the trial and error method over here to get this particular line. Directly you can connect the point number 3 and ADP, so that you can get the JSHF line, and wherever that this line is intersecting to the RSHF line, you will get the supplier point. Okay, that is what the change over here. Fine. So I hope you are clear about this particular problem. If you have any doubt, you can write down into the comment. I'll just try to explain those things. Fine. Thank you very much.